everyone. My name is Shivashankar and my roll number is 24011A0522 and our BWE faculty is Mr. G. Raju. And today I am going to talk about my presentation on representation of sinusoidal waveform. The outcomes of this presentation involves introduction of sinusoidal waveform. In this topic, we will see what is sinusoidal waveform and how does it represent and properties of sinusoidal waveform. In this topic, we will see some of the properties of sinusoidal waveform and how does it works. Phase and phase shift. In this topic, we will see what is phase and phase shift of a sinusoidal waveform and how does it calculate. Graphical representation. In this topic, we will see how the sinusoidal waveform is represented graphically in different coordinate system. Sine and cosine functions. In this topic, we will see how the sine and cosine function varies with a clear explanation of graph. Applications of sinusoidal waveform. In this topic, we will see some of the applications of sinusoidal waveforms and, and in real life situations. Superposition of sinusoidal waveform. In this topic, we will see how the superposition principle works in case of sinusoidal waveform and conclusions and key takeaways. Now, coming to the introduction of sinusoidal wave. A sinusoidal wave is a mathematical curve that describes a smooth, repetitive oscillation. It is a fundamental waveform in mathematics and physics. It is a fundamental waveform in mathematics and physics. It is commonly associated with phenomena like sound waves, light waves, and alternating current electricity. The representation of the sinusoidal waveform in mathematics is y of t is equal to a sine of omega t plus phi, where a is the amplitude and omega is the angular frequency and phi is the phase difference. Coming to the properties of sinusoidal waveform. The sinusoidal wave has several distinct properties that make it fundamental in various scientific and engineering fields. Below are some of the properties of sinusoidal wave. They are periodicity, frequency, amplitude, symmetry, angular frequency, and wavelength. Now let's talk in detail about these properties of sinusoidal waveform. Firstly, we will discuss amplitude. The amplitude represents the maximum displacement from equilibrium position. It determines wave's energy or intensity. Example, loudness in sound, brightness in light. The significance of this amplitude is it determines wave's intensity or strength. If we consider the equation y of t is equal to a sine of omega t plus phi, a is the amplitude and frequency. The frequency is defined as number of complete oscillations or cycles the wave completes in 1 second and it is measured in frequency. The formula for this frequency is F is equal to 1 by T. Periodicity, the time taken for one complete cycle of the wave. And the formula for this periodicity, time T is equal to 1 by and it is measured in seconds. And wavelength. The wavelength is defined as the distance between two consecutive points in phase. Example, peak to peak or trough to trough. and the wavelength is measured in meters, and the wavelength is denoted by lambda, given by lambda is equal to mu by f, where nu is the speed of light in vacuum and f is the frequency. And another property of the sinusoidal waveform is symmetry. A sinusoidal waveform is symmetrical about its mean value. It has two equal positive and negative halves, making it balanced over a complete cycle. Now, coming to the phase and phase shift of a sinusoidal waveform. If we consider the sinusoidal waveform equation as y of t is equal to a sine of omega t plus phi, the phase and phase shift describes the position of a sinusoidal waveform at a specific point in time, particularly in relation to another wave or a reference point. These concepts are crucial for understanding wave interference, synchronization, and signal modulation. Here in the given above equation, phase the phase of a sinusoidal wave refers to a fraction of a wave cycle and has elapsed relative to a reference point. It is measured in radians and degrees. The phase of the above equation is phi. Phase shift. The phase shift is a horizontal displacement of a sinusoidal wave relative to a reference waveform or time. It occurs when a sinusoidal wave is shifted along the time axis. A positive phase shift, phi greater 0, shifts the wave to the left. A negative phase shift, phi less than 0, shifts the wave to the right. To understand in detail about this phase and phase shift, now let's take an example. Consider two sine waves. Y1 of t is equal to sine omega t and y2 of t is equal to sine omega t plus pi by. Here, the phase angle of the first function is phi 1 is equal to 0 and the phase angle of second function is phi 2 is equal to 45 degrees. And the y2 of t, that means the second function, is phase shifted by pi by 4 radians or 45 degrees relative to y1. This means y2 of t starts earlier in its cycle compared to y1 of t. Yeah, coming to the graphical representation of sinusoidal waveforms. On XY plane, sinusoidal waves are typically plotted on a 2D graph with the time on the x-axis and amplitude on the y-axis. You can see here in the given image that the time is plotted on x-axis and amplitude on y-axis. If we consider the polar coordinates, sinusoidal waves can also be represented in polar coordinates with the angle representing the phase and radius representing the amplitude. In case of complex plane, complex valued sinusoidal wave can be plotted in complex plane with a real part on x-axis and imaginary part on y-axis. Coming to the sine and cosine function. Sine function. A sine function describes a sinusoidal wave that starts at 0 degrees. The value is 0 and cosine function is similar to the sine function but at 0 degrees its value is 1. We can see in a given graph that the red wave represents the sine function and the green wave represents the cosine function and their variations like this in the given graph. And if we see the relation between these sine and cosine graphs, the sine and cosine graphs are related by a phase shift of 90 degrees, that is pi by 2 radians. Coming to the applications of a sinusoidal waveform. The major application of this sinusoidal waveform is the sinusoidal waves are fundamental in many fields because of their natural and predictable oscillatory behavior. Here are some applications. Coming to the applications, the major application is electrical engineering. That is, the example for this application in electrical engineering is AC power supply. Sinusoidal waves are standard form of voltage and current in because they minimize energy losses during transmission. And signal processing used in generating and analyzing audio, radio, telecommunication signal. And another example for this electrical engineering is oscillator used in circuits for pro- producing steady oscillations in devices like clouds, radio, and TVs. Another most important applications of these sinusoidal waveform is in communication system. The example for this application is carrier waves. Sinusoidal signals are used on carriers in AM and FM radio, television, and cellular communication. Modulation and demodulation is another example for this application of sinusoidal waveform in case of communication system. Example, sinusoids form the basis for transmitting and receiving data in analog and digital format. Another application for this sinusoidal waveform is mechanical vibration. The example for this is vibration analysis. That is, sinusoids are used to study mechanical vibrations in engines, bridges, and buildings. And another example for this mechanical vibration is seismology. That is, earthquake waveforms are analyzed as sinusoidal signals to determine magnitude and frequency. Another application for this sinusoid waveform is audio signals. The example for this is sound waves. Pure tunes are sinusoidal in nature and they form the basis for synthesizing and analyzing complex sounds. Another example for this audio signals is speakers and microphones. Device converts electrical signals into sound waves, often sinusoidal in character. And lastly, another application of sinusoidal waveform is in physics. Example for this application is wave motion. Sinusoidal wave describe sound, light, and water wave behavior. And another example for this application is quantum mechanics. Sinusoids represents a wave function in quantum systems. Coming to the superposition of sinusoidal waveform. The superposition of sinusoidal waveform refers to the combination of two or more sinusoidal waves to produce a resultant wave. The phenomena is governed by the principle of superposition, which states that the total displacement at any point is the algebraic sum of the displacement due to individual waves. If we consider two sine wave functions with the same frequency and same phase, the resultant wave is another sinusoidal wave with same frequency and the resultant amplitude is get added as a resultant is equal to a1 plus a2 we can see here. If the two sine waves have same frequency and different phases, the resultant amplitude depends upon the phase difference. That is, it can be represented as A resultant is equal to root of A1 square plus A2 square plus 2 A1 A2 cos delta phi. Let's conclude our presentation on this representation of sinusoidal waveform with talking about some of the key takeaways like mathematical simplicity. Yes, through a Fourier analysis, any complex periodic signal can be broken into sinusoidal components, simplifying analysis and design. And another key takeaway of this sinusoidal waveform is versatility. Yes, they are used to represent AC signal, the carrier waves, and harmonic motion, forming the basis for countless technologies. And another key takeaway of the sinusoidal waveform is its applications. Yes, found in power systems, audio and video signals, medical imaging, control systems, and quantum mechanics. This is the conclusion about sinusoidal waveform.